Hello, welcome to NG Learning. This is a GCSE revision video giving a quick review of the history and the current understanding of atomic structure. And we're going to look at the history of the atomic structure through some individuals that contributed to it. There are actually, of course, thousands of people that have worked on this and expressed ideas on it, but these are just some key ones to focus in on. And particularly for GCSE, you should know about the ones here who are underlined. I'm going to start off with Leucippus and Democritus, John Dalton, J.J. Thomson, Rutherford, Geiger and Marsden, Niels Bohr, Frederick Soddy, Erwin Schrödinger and James Chadwick. So, Leucippus and Democritus were ancient Greeks. They were philosophers, so people who spent a lot of time thinking about the nature of the universe and the nature of our lives. And they lived and wrote in the 5th century BC. So about 2,500 years ago, and they proposed that all matter was composed of small, indivisible particles called atoms. So you can't cut these particles up anymore. So the word atom actually comes from a, meaning not, and temnein, meaning to cut. So something you can't cut up at all. Of course, back at those times, they were unable to test their ideas. So for the next couple of thousand and so on years, all people were able to do was to think and talk about these. But moving on in time to John Dalton, he was experimenting with chemicals and he observed that chemicals only combine in certain proportions, and he suggested that that was due to chemicals being made up of atoms that each had certain weights. And he suggested that atoms were tiny balls that could not be broken down into anything simpler. Okay, so moving on from Dalton to J.J. Thomson, and this is where we get into some more serious physics and physics experimentation. So in 1897 he was working with what are called cathode rays. So that's when we charge up a plate and we heat it and it emits a stream of negatively charged particles, and by putting those particles in a magnetic field he was able to show that they contained particles over 1,000 times lighter than the helium atom, and he called those corpuscles, but we now know them as electrons. So if we look at his experiment, so here we've got the apparatus. It's called a Crook tube, and over on the left at C is our source of our cathode ray. And through A and B we have voltage applied to accelerate those, and then between D and E we have a magnetic field applied, and over on the right there's a fluorescent screen. So as you change the magnetic field you can see how the stream of electrons or corpuscles is diverted. So you can see in the bottom right hand picture we've got our cathode ray going across on a fluorescent screen so we can see where it's travelling. And someone's bringing a magnet near, and you can see as they move the magnet it diverts the flow of electrons there, and that tells us they are charged particles. And that led us to what we call the plum pudding model of the atom. So because these electrons could come out of atoms, he said they must be embedded in the atom, and because an atom by itself is generally neutral, it doesn't have an electrical charge, it must be positive and have these negative electrons embedded in it, just like as you can see there on the left the picture of the plum pudding where we've got raisins embedded in it. We have a circle of positive charge with negative electrons embedded in it. Okay, moving on to Rutherford, Lord Rutherford, Geiger and Marsden. So some physicists. Ernest Rutherford was born in New Zealand and he worked in England and became Lord Rutherford. Hans Geiger was German and Ernest Marsden English, and they were Rutherford students, and they carried out a series of experiments from 1908 to 1913 which developed as they went along, and they fired positive alpha particles which come out of some radioactive materials at thin gold foil, and then the alpha particles would hit a fluorescent screen and they would observe that screen and see what had happened. So their apparatus looked a bit like this. So if you look at the diagram on the right, F in the middle there is our gold foil. R to the right of that is our radium, our source of our alpha particles. So they would travel across, and as they pass through the gold 4 they would hit S, which is our screen, and because these impacts are so small and difficult to see, we have M to the left of that, this tube coming out, that's a microscope, and the microscope could be spun round so we could see the impacts from all different directions. And if we look at a recreation of that experiment that someone did much more recently, their results would have looked something like this. So going along, we've got the scattering angle, so 0 on the left, where the alpha particles have travelled straight through without being disturbed, so that's happening to most of them. Okay, we've got going vertically the number of particles that were scattered, and as we go further across to the right, we still find that some of the particles were getting bounced back at extreme angles, even coming back right at the alpha source itself. So what did that tell us? Well, the fact that most of the alpha particles pass straight through tells that most of the atom is empty space. Okay, most of the atom is empty space. But a few of these particles were deflected at extreme angles, and you might remember that when we've got two positive charges, they will repel each other. So if they get it, these positive alpha particles are getting bounced right back, it means we've got a concentration of positive charge at the centre of the atom. Okay, Niels Bohr was a Danish physicist, and he mostly worked theoretically, and building on the work of a German physicist, Max Planck, he showed the presence of electron orbitals. So he had this idea of a cloud of electrons orbiting the nucleus, in particular orbital shells. Okay, Frederick Soddy is important in the history of the atom. He was an English radiochemist, and he demonstrated the existence of isotopes. Isotopes are atoms that have the same atomic number. That means that they've got the same number of protons in the centre, but they've got different atomic mass, they've got a different number of neutrons. And Erwin Schrödinger was an Austrian-Irish physicist, and he showed actually that electrons are spread out in waves. So we used to think maybe electrons were a bit like planets orbiting around a sun, but he showed they're spread out like a wave, not concentrated like a particle. Which is a hard idea, but I actually don't have to worry about that at all at GCSE. I think it's just interesting to mention. And James Chadwick showed the existence of a neutral particle that was coming out of the centre of an atom. So in his experiments in 1932, he bombarded beryllium with alpha particles, and he showed that neutral particles, uncharged particles, came out of the atom when he did that. So our current view of the atom, we have an atomic nucleus at the centre, and that is made up from positively charged protons and neutral, uncharged neutrons. Okay, so this one has 3 protons and 4 neutrons. And round the outside in our electron shells or electron orbitals, we have negative electrons. And in a regular atom, if it doesn't have any overall charge, you'll have the same number of electrons as you do protons. So here we've got 3 protons, so we've got 3 electrons. Okay, the properties of those particles, the proton, the neutron and the electron. The proton and the neutron are found in the atomic nucleus. The proton has what we call a unit charge, so an electrical charge of +1. So that's not coulombs. These are about 20 million times smaller than a coulomb. Sorry, about 2 million times smaller than a coulomb. So protons have a unit charge of +1. Neutrons have a unit charge of 0. They've got no charge. And their mass in atomic mass units are sometimes called Daltons, is 1 for both the proton and the neutron. The electrons, on the other hand, orbit around electron shells, and they're extremely small. Their mass is only about 1/2000th of that of a proton or a neutron, and their unit charge is -1, -1. And the symbols we use for those, because you might see different ones cropping up in exam papers. P plus, or occasionally actually just plus for a proton. H plus or P could be used as well. For a neutron, N by itself, or possibly N0 to reinforce the fact that it has zero charge. And for electron, E minus. Some electrons, when they're from radioactive emissions, are called beta particles, so you can also call it beta minus, or we might see E or beta without the minus there. And looking at how that would appear on the periodic table, so we have our chemical symbol, that's one or two letters, the first one always being in a capital, and if there's a second letter, that's always lowercase, that represent the element when we're looking at chemical formulae. We have the chemical name, so if you've got an English periodic table, that's the name used by English-speaking chemists for the element. So the chemical name will change between languages, but the symbol will not. We've got the atomic number, that means the number of protons in each atom. And the atomic mass, that's the average number of protons and neutrons together in an atom. And you'll notice here we've got a fraction, and the reason we've got a fraction there is because the number of neutrons actually varies on that. We talked about isotopes earlier, and there are different isotopes of lithium. So some of them will have an atomic weight of 6, and some of them will have an atomic mass of 7. And if I wanted to work out the number of neutrons, then I take that atomic mass and I subtract the number of protons. So 7 take away 3 means most lithium atoms have 4 neutrons. Okay, so some practice questions. First one, very simply, is multiple choice. Which description matches the plum pudding model of the atom? Is it A, electrons in fixed orbits surrounding a small positively charged nucleus? B, a positively charged ball with negatively charged electrons in it? C, a small positively charged nucleus surrounded by a cloud of negative electrons? Or D, solid spheres with a different type of sphere for each element? So if you want to pause the video to read through it again and have a think about your answer. And hopefully you remembered that the plum pudding model shows us positively charged balls with negatively charged electrons embedded in it. Okay, our second practice question, which is a bit more involved. In 1911, Rutherford, Geiger and Marsden carried out the gold foil experiment. They fired positively charged alpha particles at gold foil. They predicted that most of the particles would pass straight through the foil and a few might be deflected slightly. Describe what actually happened to the alpha particles during the gold foil experiment and explain why it happened, for 4 marks. And then for 1 mark, name the scientist who adapted Rutherford's nuclear model by suggesting that electrons orbit the nucleus at specific distances. So if you want to pause the video here so you've got time to write down or at least have a think about those answers. Okay, so let's go over those. So describe what actually happened to the alpha particles during the gold foil experiment and explain why it happened. So, although most alpha particles passed straight through the foil, so that's 1 mark, some were deflected at very large angles for a 2nd mark. So that's what actually happened. So now the second part, explain why it happened. This happened because while most of the atom is empty space, so that gets us a mark, a positive charge is concentrated at its centre for the final mark. And for the second part, name the scientist who adapted Rutherford's nuclear model by suggesting that electrons orbit the nucleus at specific distances, and that was Niels Bohr. And you will get away with just putting the surname, just putting Bohr. And generally with the spelling, do try and get it right, but if you get it wrong but the examiner can tell what you were trying to say, then you should still get the mark in science. Okay, our final practice question. Look at the diagram of a beryllium atom. Using correct terminology, describe its structure. So again, pause the video here so you've got time to do that. Okay, and looking at the picture, you can see we've got 5 N's in the centre and 4 pluses, so the N's are going to represent neutrons, and the plus is going to represent protons. And then we've got these dots in 2 circles around the outside that are obviously our electrons. So our answer, the atom is made up from 4 protons and 5 neutrons, which make up the atomic nucleus at the centre of the atom. Surrounding this are 4 electrons arranged in 2 electron shells, 2 in each. Okay, I hope you found that helpful. Just a couple of quick facts that you don't need to know for the GCSE, but you may find useful, or may find interesting, rather. Okay, a typical atom is only about 0.000001 millimeters across. That's 10 to the minus 10 meters. Okay, atoms, obviously we can't see them even with a school microscope. You need electron microscopes to see them. They're absolutely tiny. And the nucleus is even smaller. It's only a 10,000th of the diameter of the whole atom. So a nucleus is only going to be about 10 to the minus 14 meters across. And the mass of an atom, a single carbon atom has a mass of little over, and I'm not even going to try and read that, 0. Lots of zeros, 1 grams, or 1.15 times 10 to the minus 26 kilograms. Okay, I will be putting up more videos in the future, so please subscribe if you'd like to see those. Click a like if you found this helpful, and if you've got any feedback, that's what the comments are for. Thank you, and I'll see you next time.